This is a reminder class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate. Please don't share personal information during the class for your own security reasons. Here we go. So here's my question for today. I want to know, how can you be a better friend? What is something practical or something that you think you can do in order to be a better friend to someone around you? Go ahead, type on the board. Right? We're always thinking about what are ways that we can improve, how can we better ourselves, and a lot of those often have to do with relationships. So let's think about in terms of friendship relationships, how can we be better friends, right? So maybe it's we need to talk to them more, we need to text them right now, well, maybe not right now, maybe after class. Looking good. Yep, go ahead, tell me, what are some things that you can do? Looking good. I see answers on the board. Let's see here. Who's up here? I've got Amanda and Efren on the board. Hi, Edwin. Hi, Ethan. Welcome to class. Let's get some more people up on the board. Tony, Bradley, Jade, Orlando, Parker, Shoshana. Go ahead, get your answers up there. Same with you, Chanel, Dolly, Elias, Edwin, Ethan. Hi, Jasmine. Welcome to class. How are you doing? Hi, Jess. Good, good, good. Get your answers up there. I also see Shoshana on the board. Let's see here. Who else can we get up there? Let's get TJ and Whitney, Yoleze. I see Bradley on the board. Thank you. Let's get Matt and Michelle. Orlando, Parker. Get your answers up there. Looking good, looking good. Go ahead. Tell me, how can you be a better friend? Awesome, awesome, awesome. Hi, Dorian. Welcome to class. How are you doing? Go ahead, if you're just joining us, everyone, go ahead and type on the board, how can you be a better friend? I don't know if that's class appropriate, Efren. All right, hi, Caleb. Welcome to class. How are you? Go ahead, send you the ticket for today. All right, let's take a look at this. So you said, I don't know, I'm messing with your friends, but we care for each other. That's important, Efren. Yes, always supporting them, checking in on them, listening to them, respecting them, being grateful for them. Absolutely. Expressing that, right? Sometimes I feel like our friends might feel like they're not valued. So it's important to tell them that you value them, that you care about them, that you appreciate their friendship, right? It's important to check in on them, right? So if you haven't checked in on your friend in a while, maybe send them a text after class. Ask them how they're doing. Listening, excellent. Awesome. I love all of these ideas. Definitely this week try to... All right, yeah, Efren, let's go ahead and not talk about that right now because that's definitely not school appropriate. All right. All right, so let's go ahead and throughout this week, try to just think what's a small way that you can be a better friend to someone around you. Let's go ahead and make sure that that happens this week. So let's go ahead and jump into our content, though. We are in the May 21st attendance ticket. Go ahead, give me a green check when you have it open and ready to go. Password is in the chat box along with the links, right? It's right underneath the links. Good, waiting on green checks from Chanel, Dolly, Dorian, Edwin, Elias, Ethan, Israel, Jasmine, Jess, Jody, Justin, green checks, Letty, Miguel, TJ, Whitney, Yoleze. Efren, I did, yes. It should be in your email. Looking good. All right, everyone. I've got 11 green checks, so it sounds like we are able to get in. That's what I need to know. Perfect. All right, so today we are talking about electrons. We are starting unit number 7. We remember you only have 10 units and then the final exam, so we're already in our 7th out of 10 units, going by very quickly. So we're talking about electrons today. We will also be talking about bonding tomorrow and Thursday, and then we'll have our review game on Friday. Caleb, make sure that you're trying both links and make sure that you're typing the password correctly and it's all lowercase. Okay, if not, you might just need to save it and try it again later. Maybe it's just K12 is not working. Okay, all right, so this unit is all about bonds. So that's the focus of this unit. We're going to be talking about electrons and how they are related to bonds. We'll be talking about some different types of bonding, and we'll also talk about, all of this is leading up to our next unit in which we're going to talk about chemical reactions. So we'll touch a little bit on that this unit, but we're going really in depth with that next unit. So today's objective, we should be able to figure out how electron shells are filled in, which result in the characteristics of an atom, and we should also be able to explain how the atoms bond in order for their outermost shells to become more stable. Awesome, no worries, Caleb. You will have a quiz today. That will be the 7A quiz, and I will send that link to you at the end of class. So here we go. Atoms, remember, have these different energy levels that we call shells around their nucleus, and they try to fill them up with electrons, and their goal is to try to get those shells as stable as possible. So remember that this is the Bohr model. All right, it's not our most recent model, but it's a really good model for showing how electrons kind of occupy different energy levels in order to become as stable as possible. Okay, so the inner shells will get filled first. The inner shell here can only hold a max of 2 electrons. So that's why you only see 2 electrons right here. So really small atoms, right, their first shell only holds a max of 2 electrons. Then the next shell up holds 8, and from there on out, they, for the most part, hold 8 electrons. This is what we call the octet rule. The octet rule, or the rule of 8, where octet means 8. And this means that the shells want 8 electrons. Okay, for the most part. Again, that inner shell can only fit 2, but all the other ones want 8 electrons. Smiley faces, everyone, if that makes sense. So the octet rule, or rule of 8, shells want 8 electrons. Okay, so atoms, again, they want stable electron configurations, which means they want their outer shell to be as full as possible, right? Remember, all the inner ones will already be filled up before the outer one. So all that we're left with is the outer one that might not be completely full. So we want to make sure it's completely full. We want it to have 8 electrons. So for example, take a look here. Count up how many electrons you see on the outer shell of fluorine here. Go ahead, tell me in the chat box, count them up. The outer ring only. You don't need to do the inner ring. Ignore the inner ring. Count the outer ring and tell me how many electrons do you see here. Count them up. Not quite 6, not exactly 6. There we go. Thank you, Efren. Thank you, Caleb. Again, count those up on the outside ring. Excellent. Yes, thank you for all that participation. Yes, you should see 7 electrons on the outermost ring, and this one can fit up to 8. And so in order for fluorine to be happy, it needs to get an extra electron to fill it up to 8. Smiley faces if that makes sense. So there's a missing electron here that fluorine wants in order to become stable. So it's not stable yet. Once it gets this extra electron, then it will become stable. Excellent. All right. So that being said, this idea of the outermost shell and the number of electrons that it has is the reason that different types of elements on the periodic table of elements have very similar properties, okay? So what ends up happening is all of the atoms in the same column have the same number of valence electrons. So you can see here, this first column, they all have 1 electron on their outermost shell. Okay, smiley faces, everyone, if that makes sense. Now, as you go up, they end up with more and more shells, but their outermost shell, the only shell that really matters, is the outside one, and they only have 1 electron on that outermost shell. Okay, same thing with this next column. They have 2 on their outermost, all the way to the right, where these ones on the right have 8 on their outermost shells. Okay, so the result is the outermost shell gives these elements similar properties. So for example, in group number 7, we have fluorine, chlorine, and bromine, and and iodine, and all of these elements are very similar in that they form salts by reacting very quickly with any atoms that have a single spare electron, right? They already have 7 electrons, they just need 1 more. So if they can find an atom that has 1 electron to spare, they're going to grab that electron really quickly, and they're going to be very reactive and form a salt. Okay, thumbs up if that's beginning to make sense. So if they're in the same column, they have similar properties because they have the same number of outer electrons. Okay, so let's go same column, similar properties because they have the same number of outer electrons, also called valence electrons. I know, it's a lot of information. All right, this is number 1 in your ticket. Go ahead and give me a green check when you have this saved. We're going to go over some examples. 30 seconds to fill in the blank with the word similar. Give me green checks. Go, go, go. Need some more green checks. Waiting on Tony, Ashton, Chanel, Damien, Dylan, Edwin, Elias, Ethan, Jacob, Jackie. Thank you, Jackie. Jess, Caleb, Letty. Green checks, please. Miguel, Rozzy, Whitney, Yolese, No worries, Jacob. Welcome to class. I don't know what you're asking, Efren. Group 1, right here, column number 1, they only have 1 electron on their outermost shell. Group 2, right here, the column 2, only has 2 electrons on its outermost shell. So the number at top tells you how many electrons they have on their outermost shell. Sorry if that's confusing. So this one has 1, this one has 2, this one has 3. These elements have 4 on their outermost, these elements have 5, these elements have 6, 7, and 8. So the number up here tells you how many electrons they have on their outermost shell. Does that make a little bit more sense? Yeah, it's not opposites, but yeah, on the outside, exactly, on the outermost shell. Okay, so I'm going to show you some examples and that will begin to make a little bit more sense, Efren, okay? All right, so let's go ahead and take a look at this one. Let's take a look at carbon together. So we need to figure out the number of valence electrons. And what does valence again mean? Does that mean inner electrons or outer electrons? Tell me in the chat box, does valence mean inner or outer electrons? What are we focused on here? What do we care about? Tell me in the chat box. I see Caleb chatting. Yeah, this is a little bit from unit, a review from unit 5, which is the one where I just had videos because I was testing. So if you need to, you can go back to those ones and that should help you figure that out. All right, yeah, so the outer shell is the one that we're looking at. So we're looking at the outermost shell here, okay? And we're ignoring this inner shell right here. Smiley faces everyone if that makes sense. So ignore the inner shells. We only care about the outermost shell. Outermost shell. Okay, awesome. So taking a look at that outermost shell, go ahead, count up for me. How many valence electrons do you see here? Yep, exactly. The second shell for this one is the outermost shell. But you'll know that when we get down to sulfur, for example, the second shell is not the outermost. So that's why I'm saying outermost shell, because that's the one that we care about the most. Yeah, all right, everyone. So take a look at this outermost shell. Count up for me. How many electrons do you see on carbon? How many electrons do you see on carbon? I got an answer from Efren. I need way more participation. Come on, guys. This is a quick lesson, but only if you're actually participating. So if you want to get out of class early, you want to learn quickly, I need your participation. Awesome. Thank you, Israel. Thank you, Caleb, Jasmine, Dorian. Yes, the outermost shell here currently has 4 electrons, right? We can count them up. We can see 1, 2, 3, 4 of them right here. So we've got 4 valence electrons. And remember, this outermost shell can fit how many in total? Remember, it's called the rule of what? How many in total can we fit on this outermost shell? In total. Yes, the octet rule. Yes, in total we could fit 8, right? But we need to figure out how many then are missing to get to 8. So 4 plus what will get me to 8? Okay, so the question now is 4 plus how many do I need in order to get to 8? How many do I need here in order to actually fill the shell and become stable? Yeah, exactly. So we're missing 4, right? So we need 4 more. Need 4 more electrons. Electrons to become stable. Okay? Give me a thumbs up, everyone, if that's beginning to make sense now. Yep, 4 plus 4 will give us 8. All right. Looking good. All right, so now let's take a look here for sulfur. Again, only looking at the outermost shell, so we want to ignore shell number 1, ignore shell number 2. We're just looking at this outermost shell. Tell me, count those up. How many electrons do you see on the outside of sulfur? How many valence or outer electrons do you see on sulfur? Awesome. I see an answer from Amir, from Caleb, or sorry, from Efren, from Caleb. Awesome. Efren's just getting ahead of us here. How many valence or outer electrons do we see on sulfur? Do we agree with Efren? Do we disagree? And Caleb, do we disagree? I only have 2 answers. I need more participation. Go ahead, focus, get in your chat box. How many valence electrons do you see for sulfur? Number of electrons on the outermost shell. Let's get some answers from Amanda, Amir, Andrea, Tony, Ashton. Let's hear from Bradley, Chanel, Damien, Dolly, Dorian, Dylan. Thank you. I see Dorian typing. Let's hear from Edwin and Isaiah. Let's hear from Elias, Ethan, Israel, Jacob. Again, number of electrons on the outermost shell. There we go, there we go. Let's hear from Yoleze, Whitney, TJ. Awesome, thank you, Israel. There we go. Thank you, Bradley. I see Dorian typing. Yes, you should see 6 electrons on the outermost shell for sulfur, right? So we should see 6 here, right? 1, 2, 3, 4, 5, and 6. So again, we need to figure out 6 plus what will get us to 8, because the shell actually wants 8 in total. So 6 plus what will get us to 8? Tell me in the chat box. How many more do we need? How many more do we need? Yes, we need 2 more electrons. Yes, 6 plus 2 will get us to 8. So we need 2 more electrons to become stable. Excellent. All right, give me a green check now if this makes a little bit more sense when we're talking about the outer shell, valence electrons, and stability, how we become stable. Excellent. Thank you, Shoshana. Looking good. Thank you, Efren. Love it. Looking good. All right, everyone. So that being said, so again, valence is determined by the number of electrons in the outermost shell. And again, this is going to determine how it reacts. All right. It determines its characteristics, how it reacts with other things. Okay. Now let's talk a little bit more about those innermost shells, right? So there are shells inside underneath the outermost shell. Now, for the most part, those aren't that important when it comes to bonding, but you do need to know that they do kind of buffer the outermost shell from the positively charged nucleus, which means that as you get further and further away, because there's more and more shells between you and the nucleus, it's a little bit easier to tear away these electrons. All right, so because remember, these electrons are attracted to the nucleus. Electrons are negative, the nucleus is positive. So if you get further and further away, they're not as attracted and it's easier to pull them off. Thumbs up if that makes sense. Okay, so if you have many inner shells, right, so big atoms have many inner shells, making it easier to take an electron from the outermost shell. Okay, so we'll talk a little bit more about that when we talk about periodic trends, but I do want to kind of just introduce that idea right now. Now again, the outermost shell, we also call that the valence. So again, the valence is the number of electrons in the outermost shell. So for example, you can see right here, oxygen currently has 6 electrons, just like sulfur did, and oxygen and sulfur react very similarly. And oxygen needs to gain 2 more electrons to be filled. Sometimes atoms can also lose electrons to fill an outermost shell. So if they only have a couple electrons, it's actually easier for some electrons to just lose all of those electrons. That way they have a full outer shell below. Okay, so we'll take a look at that as well. All right, so this is the whole reason that we're talking about this. This entire unit is all about bonding, how atoms connect and bond together. And the reason that atoms connect and bond together is because of this idea of stability. So atoms are going to either gain, lose, or try to share electrons in order to fill their valence because they want to be stable. So by sharing or by gaining or by losing electrons, they can become stable through this process of bonding with each other. So let's take a look at water. Water is a really great example. Take a look at hydrogen. How many electrons do you see on the valence of hydrogen? Tell me in the chat box. How many electrons do you see on the outermost shell of hydrogen? Thank you, Efren. Thank you, Bradley. Thank you, Israel. Yeah, so hydrogen has 1 valence. Okay, and both of these would have 1, right? So hydrogen has 1 valence, and so does this hydrogen. Now, these are small atoms, so they actually only have 1 shell. So instead of the octet rule, remember that for this very tiny, tiny shell, they actually can only fit 2. So if they can only fit 2, how many more does hydrogen want? If they can only fit a total of 2 for hydrogen's ring, how many more do they want? Yeah, so they want 1 more, right? So they have 1 valence and they want 1 more. Want 1 more. Want 1 more for a total of 2, right? So we want a total of 2. Okay, smiley faces everyone if that makes sense. Again, the reason hydrogen's a little bit different is because it's much tinier. Okay, this tiny first shell can only fit 2. All right, now oxygen on the other hand, all right, oxygen, how many valence does it currently have on its outer shell? Okay, yes, it has 6 valence, excellent. And this one does follow the octet rule because it's much larger. So how many more does it need to get to 8? Right, it wants 8 in total, so how many more does it need? Yeah, it needs 2 more, wants 2 more for a total of 8. Okay, so the question is, how on earth can we actually get to these correct totals? All right, how do we get hydrogen to get that extra electron? How do we get oxygen to get those 2 extra electrons? Well, the trick is here we can actually get them to share electrons. And by sharing electrons, not only do they bond together, but they also become more stable because now they feel like they have the correct number of electrons. Exactly, Efren. So take a look at this. For this hydrogen, he's going to actually share his white electron right here with oxygen. And oxygen is going to share one of its red electrons right here with hydrogen. Obviously, in real life, they're not colored, but for the purpose of this diagram, this helps us better visualize it. So then, once they share these electrons together, go ahead and follow the circle around hydrogen. From hydrogen's perspective, based on what hydrogen sees, how many electrons does hydrogen now see on its own ring? Follow the ring. How many electrons are now actually on its ring? How many electrons are actually on hydrogen's ring now? Now that it's sharing these with oxygen. Tell me in the chat box. Yeah, exactly, Dorian. Exactly, Efren. So now it sees 2, right? So it sees, right, in parentheses, it sees 2 valence electrons. And so now, is it happy? If it sees, like, it feels like it's got 2 electrons on its ring, is it now happy? Is it now happy if it feels like it has 2 on its shell? Tell me in the chat box. Yes, no. Is hydrogen now happy now that it feels like it's got 2 valence electrons? Yeah, exactly. So hydrogen's going to be very happy now. So hydrogen's happy, hydrogen is stable. So now hydrogen is happy / stable. All right, same thing with this other hydrogen, right? So it also will share its white electron with oxygen. Oxygen shares one of its other red electrons with hydrogen. And now when we follow hydrogen's ring around, or shell, it looks to this hydrogen as though it has 2 valence, right? So again, this hydrogen is also happy. It feels like it sees 2 valence, and therefore it's happy / stable. Awesome. All right, so now let's take a look at oxygen. All right, follow the ring around oxygen and tell me how many electrons does oxygen now have on its ring? Through this process of sharing, how many electrons does oxygen now think that it has? Yeah, if you actually see this, these white electrons are now on its ring as well. So now it's actually feeling like it has 8 electrons in total, right? So it sees 8 electrons, 8 valence electrons. And so now oxygen is also happy and stable. All right, so at this point, all of these atoms are stable, and so this makes a very, very stable molecule that is completely happy and can exist easily within our world. That's why water is able to exist in our world and stable, and it doesn't break down because it's happy, because the oxygens and the hydrogens are all happy. Yeah, so because they're sharing their electrons, they have to bond together and they have to stick together. So if they weren't bonded together, then they would not be stable. So only by sharing and sticking together are they actually able to be happy. Okay, thumbs up everyone if this process makes sense. This is the purpose of bonding, to help atoms be stable. To help atoms be stable. Smiley faces. Awesome, thank you, Caleb. So there are things that can cause it to become unstable, Efren, but in that case, it would immediately react with something else to become stable again. So it's very rare to just have a free hydrogen that's not bonded to anything. In fact, hydrogen as a gas exists connected to other hydrogens naturally. So you don't actually get hydrogens by themselves in our universe naturally because they'll automatically bond with the closest thing next to them that can spare another hydrogen or can spare another electron. Good question. All right, everyone, go ahead and match these up on the whiteboard. What's the purpose of inner shells, outer shells, and bonding? Go ahead, get your answers up there. Use the line tool. Any color but red, please use thin lines. Excellent. I see Efren on the board, Dolly on the board, Israel on the board. Make sure you are participating. Working quickly. Thank you, Amanda. Dorian, Jacob, Tony, Caleb. Awesome. Love that participation. Thank you, TJ. Looking good. All right, there's so many I can't see anymore. There we go. All right, I'm going to go ahead and pause these tools, shrink these down a little bit. Let's take a look at the correct answers here. What if we run out of what? Specifically, run out of water? Yes, if we ran out of water, we would die. Electrons? I mean, without electrons, you would have no cohesion, right? Because without electrons, there's no possibility of bonding, and your body is made up of a bunch of bonds, right? There's a bunch of molecules in your body that make up who you are, and all of those are due to the bonding due to electrons. So without electrons, all cohesion within our universe is lost, right? Same thing with protons, right? Protons are the identity of atoms. So if you lose protons, then you no longer have any idea, and like each of these has no identity. So you would have no oxygen or carbon for your body because it would no longer have that same identity. So you need all of it. You need all of it. And it's not going to disappear, right? Matter just doesn't disappear. All right, so inner shells. Yes, the purpose of inner shells is to buffer the valence electrons from the nucleus. Excellent. Those outermost shells have the valence electrons, right? Valence means outermost. And bonding, the purpose of bonding is to help atoms become stable by gaining, losing, or sharing electrons to fill their shells correctly. Excellent job. All right. So all of that being said, everyone, so the chemical properties of an atom, again, are determined by their valence electrons. The valence electrons, if you haven't figured out, are very important because they determine the atom's ability to gain or lose electrons, which is the chemical properties of an atom. So chemical properties are due to valence electrons because that figures out whether or not they gain or lose electrons in a reaction. Now, that being said, if you take a look over here, okay, atoms on the left actually lose electrons very easily. So if you remember back to that chart that we saw at the beginning where I had the different columns numbered, the first column only has one valence electron, okay? Now, if you remember the octet rule, in total it wants 8. So let's think about this. If it only has one electron and in total wants 8, how many more would it need to get in order to get to 8? Tell me in the chat box. Okay, so this first column has one electron, okay, one valence electron, and in total it wants 8. So how many more would it need? How many more would it need? Awesome, I got an answer from Efren. If it has one, wants a total of 8, 1 plus what gives me 8? Yeah, I would want 7 more electrons. However, it's really hard to get 7 more electrons. That means that you have to be stealing 7 electrons from other atoms, and that takes a lot of energy. So instead of stealing 7 additional electrons, what happens here is this first column actually will just lose that 1 electron. Okay, thumbs up if that makes sense. So by just losing that 1 electron, it goes down to a shell below it, and that shell is already filled. So it has 1 electron, so it just loses 1. So loses that 1 electron and goes down to the filled inner shell, the shell that's right below it. Sorry, Whitney Cash, we should not be putting answers to the attendance ticket in the chat box. All right, if you ever miss anything, if we have time at the end of class, I can go back to the slide, or it's always in the recording. But I always want you to actually see what it was filling in, all right? Yeah, so Brianna, you'll need to go ahead and watch the recording later on, or I can go back to it after class. But as always, we should never put any answers in the chat box. All right, thank you, everyone. Okay, so same thing with this second one, right? The second one has 2 electrons, and again, to get to 8, it would have to gain 6 more. But instead, it's much easier just to lose 2. Smiley faces, everyone, if this is beginning to make sense. So if you have 1, 2, or 3 electrons, it's much easier just to lose those few electrons than have to gain many more. As we get over to this side on the right where they have more electrons, so for example, nitrogen group has, let's see here, it has 5 electrons. This one has 6 electrons. This column has 7 electrons. For all of these ones, it's much easier for them to just gain a couple electrons to get to 8. Okay? Dolly, no. Again, do not put any answers in the chat box. All right. All right, so here we go, everyone. This is number 2 in the chat. In the ticket. Go ahead, take 30 seconds to answer that. You should be filling in the blank with the word valence. Go, go, go. This is number 2 in your ticket. Excellent. Waiting on green checks from Amir, Ashton, Bradley, Damien, Dylan, Edwin, Elias, Ethan S. Sorry. Thank you, Jacob. Waiting on Jasmine, Cash, Letty, and Matt, Miguel. Green checks for number 2. Awesome, awesome, awesome. Yeah, so Efren, at some point it becomes very difficult to pull electrons away because as you get too many protons, right, as you pull away electrons, you still have the same amount of protons in the center. And so as you get less and less electrons, those protons become, in comparison, stronger and stronger, right? If we have 6 protons, 6 electrons, they're about even. But as you start pulling away electrons, let's say now you have 3 electrons and 6 protons, those positive protons are going to pull really hard on those electrons, and it's really hard to rip those electrons away. Excellent. All right, everyone. So let's go ahead and make sure that this makes sense. What I want you to do, go ahead and use your box tool or your circle tool, and I want you to circle in the correct terms here. So atoms on the left have less electrons, so they are better at losing or gaining electrons. And then atoms on the right have more electrons, so they are better at losing or gaining electrons. Go ahead, circle those on the whiteboard, and then we'll go over that topic together. I see Dolly on the board, Israel on the board, Caleb on the board, Dorian, Jacob, thank you. I know, atoms can be very, very confusing. I see TJ on the board, Amanda on the board. All right, going to pause your tools in about 5 seconds. 2, 1, and pausing. All right, so both of these are actually incorrect, okay? So I'm going to go over why both of these are incorrect. All right, so atoms on the left have less electrons, right? So they only have 1, 2, or 3 electrons. Now again, remember that all atoms want a total of 8 on their outermost shell, unless they're very, very tiny. But for generalization purposes, all atoms want a total of 8. So if you only have 1, 2, or 3 electrons, is it easier to gain a whole bunch more to get to 8? Or is it easier just to lose the couple that you have? Tell me in the chat box, is it easier to gain a bunch more or to just lose the few that you have? Tell me in the chat box. Yes, I see Efren's got an answer for me. So atoms on the left already only have a few electrons, so is it easier to have to gain a bunch more to get to 8 or to lose the few that they have? I see Dorian typing. Yes, thank you, Oscar. Yes, it's much easier to lose the few. So it's much easier to just lose the few electrons they have. Okay, smiley faces if that makes sense. So atoms on the left, because they already only have a few electrons, they're much better at losing their electrons. They want to give electrons away. They want to give the few that they have already away. Now, on the other hand, atoms on the right have more electrons, right? They have 5 or 6 or 7 electrons. So in this case, is it easier for them to have to lose all of their electrons, 5, 6, or 7, or to just gain a few more, right? They would only need to gain 3, 2, or 1 more electrons. Which one is easier, having to lose all their electrons or gain a few more? Tell me in the chat box. Lose all their electrons or gain a few more? Yes, it's much more easy. It's much easier just to gain a few more. So in this case, it's easier to just gain the few more electrons, the few electrons they need. All right, thumbs up everyone if that's making sense. So in this case, I know it's kind of the opposite way to think about it, but that's one that we frequently get wrong, so I want to make sure that we understand that. Awesome, thank you, Arrow, thank you, Caleb, Jacob. Perfect, all right. So sorry, yes, Efren, so that is yeah, you're right. So once they give away or take electrons, that's the process of bonding. And we'll see tomorrow that when 2 atoms bond, one will give away electrons and the other one will take them. And by doing that together, they create a bond as well as they both are now happy and stable. So again, that's the purpose of bonding, right? Now, here's the thing. We did see on one of the columns all the way to the right that one column already had 8 electrons. So if they already had 8 electrons, are they happy based on our octet rule? If they already have 8 valence electrons, are they happy based on our octet rule? Yes, they are. So these are what we call the noble gases. So the noble gases are the column all the way on the right, and those are helium, neon, argon, krypton, and xenon. And these ones already, you can see on their outermost shells, they have as many electrons as they can possibly have, right? Helium's a tiny one, so it has 2, but all these other ones have the correct valence. They have 8 electrons on their valence. So because they have full shells, they are very, very stable and they do not want to react. So these atoms just exist by themselves, and it's very difficult to get them to bond with any other atoms because they're already happy and they're already stable. Xe is xenon. xenon. All right, so this is number 3 in your ticket. Go ahead and give me a green check when you have it saved. You have 30 seconds. Ready, set, go. Again, these ones are already happy. They're happy singles. 20 seconds, everyone. All right, waiting on green checks from Amir, Ashton, Bradley, Chanel, Damien, Dylan, Edwin, Efren, Elias. Thank you, Jasmine. Waiting on Justin, Caleb, Letty, and Yoleze. This is number 3. Fill in the blank with the word full. Ow. All right, looking good. Here we go. All right, so last thing that we need to talk about is that when we draw atoms, at some point the atoms get really, really, really big. All right, so I can show you, for example, this one right here, an argon atom, is a really big atom. So you can see that to fill in all of these electrons on their innermost shells, if I wanted to draw argon like several times, do you think that would be easy to do, to have to continuously be drawing all of these extra atoms on the inside? Tell me in the chat box. If I had to draw this a bunch of times. No, it would not be easy. So once we get to these bigger atoms, it becomes a lot less convenient to have to draw them. So instead we have what's called the Lewis dot diagram. And the Lewis dot diagram only represents the valence electrons, only represents the outermost electrons. And so for that reason, it's much easier to draw the atoms this way than to have to draw all of their inner shells as well. Thumbs up, everyone, if that's beginning to make sense. So this way, we don't have to draw the inner shells. Okay, so we don't have to draw the inner shells. And this actually is really important because when we talk about bonding, you guys won't experience this as much, but in future chemistry classes, you'll probably experience this if you take a future chemistry class, that you have to do a lot of drawings for how atoms bond, okay? So if you had to draw all their inner shells, it would take a really long time and you would probably never be able to answer a question because you'd be too busy drawing. So doing this just makes it a lot easier. So what we do is we take the name of the element, like Li, or the symbol for the element. Li means lithium, C means carbon, O means oxygen, and then we just draw dots on the outside, kind of like in a square around the element symbol based on its number of valence. So take a look here. You can see lithium has 1 valence electron. So it's got 1 dot. Carbon has 4 valence electrons, so it's got 4 dots. And oxygen has 6 valence electrons, so it's got 6 dots. Okay, but again, we ignore all of the inner shells. We don't need to draw those electrons. One more time, thumbs up, everyone, if that makes sense, because you will see Lewis dot diagrams in the future as we talk about bonding. Thank you, Arrow. Thank you, Caleb. Perfect. Thank you, Dolly. Awesome. This is number 4 in your ticket. Give me a green check when you have it saved. You have 30 seconds. Ready, set, go. Fill in the blank with the word only. Yes, if you take chemistry in college, you will do many Lewis dot diagrams. Yeah, no, college chem classes are a lot of fun because you actually get to be in person for all the really cool reactions that they do. So we do demos and stuff in my class, but a lot of that's either virtual or I'm the one doing it. But in college, you get to be the one that's actually doing a lot of the really cool reactions. Like when I was in college my first year, we made the Laffy Taffy artificial banana smell. We synthesized the artificial banana smell. It was really great, and the entire lab smelled really delicious. All right, waiting on green check from Amir, Ashton, Bradley, Damien, Dylan, Edwin, Elias, Jasmine, Cash, Letty, Matt, and Yoleze. Green checks for number 4. Not a Laffy Taffy, though, just a banana. Awesome. All right, everyone. So today we talked about electron shells. How they get filled is the results and the characteristics of atoms. We talked a little bit about bonding in order for outermost shells to become stable. That is the purpose of bonding. Awesome. So I'm going to go ahead and send you your quiz really quickly. So here is the quiz. Remember, all of the answers to the quiz, you can actually also find the information in the attendance ticket. So do them side by side and submit them at the same time. And here you go, everyone. Here is the last word for your ticket. Last word is neon, and I will see you all later. Bye, everyone. Here's the ticket password again if you need it. Bye. Thank you. Have a great day.